is true in many, many cells, whether they're cancer cells or non-cancer cells, embryonic cells. In order to divide, they need to have a small electrical potential. Now, what does that mean? Well, if the electrical potential is due to EZ water, and you have a small electrical potential, it must mean you're missing a lot of EZ water. And the cell can't function that way, and many pathologies arise, including cancer. And so the implication is that this needs testing, obviously, but the implication is if we're on the right track, then it's not complicated to reverse cancer. All you need to do is build EZ water.
Well, Gerald Pollack, thank you so much for joining me.
I'm really happy to do that.
And I want to start off this podcast and this conversation just by thanking you. I'm very grateful to people like you and to you specifically for your work going against the grain and doing, following truth wherever it leads you, despite criticism and ridicule. And I'm very happy that you're receiving the recognition that I believe you deserve. So I want to thank you for the work that you've done so far.
Well, and thank you for your kind comments. Much appreciated.
Yeah. So we're going to talk a lot about water, I imagine here. And maybe to start us off, I'd love to know actually, I'm going to start us off maybe backing into or reversing into why water is so important. But I've heard you say that, when talking about Gilbert Ling, who you encountered initially, that if he was right, then all of biology is wrong. And so I wonder if you would just let me know and my audience know from your perspective, what do we have wrong? Maybe we can start there and then back into...
starting with Gilbert Ling. Gilbert Ling, who passed, unfortunately, about 5 years ago, his main thesis was that in cells, the water was not the same as liquid water as we know it. Liquid water as we know it, the molecules are randomly oriented and bouncing around a fierce number of times per femtosecond. But he said, no, that's not true. The molecules are actually organized or structured or lined up, like soldiers at attention. And now, the textbook view is that the water inside the cell is liquid water, nothing different from liquid water. And if it's liquid water, that means that molecules could diffuse freely. But molecules can't diffuse freely. And all the interactions that are discussed in the books on cell biology or biochemistry make the presumption that any molecule in a cell is diffusing around and bouncing around and therefore enabled to encounter other molecules and react. If Gilbert Ling was right about water molecules acting as like soldiers at attention, that can't be the case. And so the very premise on which cell biology is based, Gilbert Ling said, no, it doesn't work that way at all. So the two views are completely different. Of course, in Gilbert Ling's view, there has to be it can't the cell can't persist that way because nothing will ever happen. It's sort of like a cell built of ice. So something has to happen. And I addressed that in the first book on water that I wrote, Cells, Gels, and the Engines of Life. And what I tried to demonstrate that there's a lot of evidence in the half dozen different kinds of cells, important cells, muscle cells, nerve cells, secretory cells, that what happens is that in the relaxed cell, it's just sort of like Gilbert Ling thinks, although we found some features that are grossly different from what Gilbert had been espousing, and features that are really important. And if you ask me about them, I'll tell you. But what happens is that in the relaxed state, think about a muscle cell, for example. In the relaxed state, the muscle's not contracting, and all the molecules of water are somehow organized, lined up, not exactly the way Gilbert Ling has suggested, but pretty much. And then what happens is that the water and the proteins undergo a phase transition. Everything changes. And phase transitions are well known to chemists, physical chemists and such. It's kind of standard. But in biology, people never heard of it. But that's what happens. And we provided ample evidence for that in various kinds of cells. So in the case of the muscle cell, if the muscle cell wants to contract, what happens is the cell undergoes a phase transition from the state in which the water is ordered and the proteins are in their extended state, doing nothing. And then the transition occurs and everything changes. What happens is that the structured or organized water undergoes a change to ordinary liquid water. And the proteins then undergo some sort of configurational change that represents the action of the cell. And a muscle cell would mean that the proteins are undergoing some sort of change that produces the contraction. And then when the contraction is over, the whole system reverts once again, a reverse phase transition, back to the initial state in which the water molecules are ordered. So that's at least our interpretation of Gilbert Ling's ideas, and that is grossly different from what the cell biology or biochemistry book argues is the case. I hope I've explained it.
Yeah, maybe I could share with you my interpretation of some of the science, because I could be wrong. I'm not a trained scientist.
We all could be wrong.
Yeah.
Scientists, you're not.
Yeah, well,
trained scientists are often wrong.
Yeah, unfortunately, all too unwilling to admit that a lot of the time, but that's why I appreciate you and your work. So I see so many implications here for, just speaking to maybe my audience, because I'm in the healing arts world, that there are so many implications here that we don't understand, even as you're saying, maybe muscle contractions, what you've looked at in the modern, the modern consensus of it, for things like muscular dystrophy or multiple sclerosis or Parkinson's or all these so-called diseases that involve apparent muscle contractions or the inability to contract muscles or muscle spasming, uncontrollable spasming. And what we've been told is that muscles contract because a signal is sent from the body to the brain, and then a command is sent from the brain back to the body, and then that contracts a muscle. But it doesn't explain why a jellyfish can propel itself through water without a brain or motor nerves, so-called motor nerves. So, and I love that. I don't know if you speak much about jellyfish, but I love the imagination of it. There's so many examples of the work that you do out there in nature for us to observe, but a jellyfish might be one of them. They're made of gel.
we haven't focused on jellyfish, but it's interesting that some jellyfish, 99% water.
Yeah.
And they function pretty well. And so that is, you might say, indirect evidence for the importance of water. Water is doing something. Maybe we don't understand everything that water does, particularly in jellyfish, but it's got to be important. And if you, we're not 99% water. We're 2/3 by volume. But actually, if you convert that to the fraction of molecules that are water molecules, the number actually is something like 99%. To fill that 2/3 volume of water, you need a lot of small water molecules to do it. And if you do a molecular count, if you just line up all the molecules in a typical cell, like a nerve cell or a muscle cell or whatever, the count comes to more than 99% of molecules are water molecules. And, in the cell biology book or biochemistry book, says it usually they open the first chapter with water, and water is really important, and then the rest of the book ignores water completely. And the implicit argument is water is really nothing more than a substrate to hold the more important molecules of life. And what we found is that that's completely untrue, that water is absolutely central for all of life, as apparently it is for the jellyfish. There's not much else.
Yeah. Yeah. Well, those characteristics are shared by fascia, which is what I've been studying, working with, I think. I'd actually love to selfishly ask you some questions that could illuminate the work I've been doing while I have you here.
Well, I hope I can contribute. It hasn't been the focus of our attention, but yeah, fascia is so.
Well, yeah, you mentioned all throughout The Fourth Phase of Water, which I highly recommend everybody read who's listening to this. Well, it's an excellent book. It's easy to read. And there's so many examples that we can, try ourselves or observe in nature. One of my favorites is going to the beach. Such a good one to look at the sand. But all throughout that book, you talk about the extracellular matrix, which is, according to fascia science anyway, housed inside the fascia. So that seems very important. And of course, we used to just take the fascia out when studying the human anatomy, let's say, and actually even most of fascia science, unfortunately, has been conducted through cadaver research, where they drain the body of the fluids. So then they're studying what's left. Yeah. I know we have a short bit of time, so I'm gonna selfishly ask you a couple of questions here, see where it takes us. So I've been since 2010, 2011. That's when I first started experimenting with a form of compression and shearing of fascia in the body, or I don't even know actually. And then I encountered your work, and it made me wonder: are we even working with fascia, or are we just working with water molecules, like, compressing and shearing the water that's in the body? And does that matter? I mean, I think the truth matters. But people report feeling lighter and buoyant. That's a big word. I feel buoyant. I feel lighter.
When what happens? When?
So it's me stepping on people.
Stepping on.
And then yep. So so it's a lot of pressure or a lot of compression, where I pin their tissues to the bone, not all the way to the floor, so they have full range of motion. And then they perform movements under my foot. And so their tissue is between their bone and my foot. So you can imagine me stepping on your quad, for example, and then you would move your quad, your legs in and out. And the tissues between my foot and your femur would there would be a shearing effect happening. And it produced rapid results for so many of my clients in pain, where they got out of pain. They reported feeling lighter and more buoyant. And I had no idea why. And so I had all these theories about it until I read your book, and because you talked so much about compression and shearing. So I wonder if you could just share what, that compression or pressure, what effect that has on water in our bodies.
You asked a difficult question. I've never thought about it, well, we found that. Well, first of all, the fascia is full of proteins which bind water, which means that there must be easy water associated with the fascia. And we know that if you exert pressure, you build easy water. We found that when we were looking at hyperbaric oxygen therapy, which is high oxygen, high pressure. And we did experiments, and we found that if you apply high pressure, you convert liquid water into easy water. So although you don't weigh too much, I suppose if I stood on, I would have a more appreciable effect. But what I could imagine, again, this is purely hypothetical. I never thought about this question, is that by exerting pressure, you're building easy water. One of the issues is when you deal with fascia is the transport of water. you've undoubtedly seen the films of the water moving by, what's his name, the French name, Jean-Pierre Gomberto or something like this. Have you seen that?
I don't know if I have. I may have.
Well, it's pretty dramatic. You can see the water moving along the fascia, not dehydrated, but real fascia. It's quite fascinating to see. So, if you step on the fascia, you exert pressure, you build easy water. If you build easy water, you facilitate transport because we know we have experiments that demonstrate this. That if you have for example, a tube made of hydrophilic material, and it's filled with easy water, you can see flow that occurs in the core of the tube. And in order for that to happen, you must have easy water. The easy forms a kind of ring-like annulus just inside the tube. So I could imagine something similar happening in the fascia. That you step on it, it builds easy water because pressure builds easy water. And if you have easy water, then that facilitates transport. And transport is important in the body, all kinds of flows. And the mechanism that I was alluding to, I think we demonstrated, actually recently published a paper a few months ago, that this applies in the cardiovascular system. We didn't study the fascia in this; we studied the cardiovascular system, and the finding, which is kind of radical, you might say, we found that the flow in the cardiovascular system is propelled not only by the heart but also by the vessels, by the mechanism that I've been talking about. So, I'm thinking, in response to your question. That when you step on the fascia, so interesting a maneuver, you're facilitating flow, and flow is important, and flow is important in restoring tissues to their natural state. If you have no flow and everything is stagnant, then the tissue is not going to perform as well as, an example is the cardiovascular system. You need the flow. And I think you need the flow in the fascia too. And so pure speculation, I'm not sure, is that by exerting pressure, you're facilitating flow, which improves function.
Well, this is why I think your research is so important because, and you've talked about, you've focused on the science and following the truths, but there are so many practical applications or technologies, whether it's, a human technology like me, a methodology, stepping on people, or other water filtration technologies I've heard you talk about that could be explored and theorized about and then produced as a result of what we know about water. So,
well, what an amazing maneuver. How did you ever come to think of this?
Well, I learned something in 2008 that was a pin and stretch method involving stepping on people, but I intuitively started, I didn't like personally being pinned to the floor, and I never felt light and buoyant after. So I started with my clients experimenting with compression and shearing. So I would pin the tissue only to the bone, so that way not all the way to the floor, and then I would allow people full range of motion. So their joints could perform a full range of motion under compression. And that's when people started reporting feeling light and buoyant. So there's something also about the shearing, and it makes me think of, I always tell people to go look at the beach, because right where the water, as you describe in your book, and then as we can all observe if we go to the beach, as the wave crashes up and then recedes, there's a shearing effect happening. And that water, we don't think about it often, but it's sort of it defies what we would normally think is logical, because that's where most of the water is, and yet that's where the sand is the most structured, or harder. It's actually harder there rather than sopping wet, which is fascinating. So, your research makes me think of something else I've been thinking about a lot, which is altitude's effect on our flow. I don't know if you've ever thought of this, but do you play tennis?
I used to recently. You
have you? Not very often, but I have. But tennis players need to bring different tennis balls, if they're going to play at elevation, because they travel farther faster.
Yeah.
With less pressure, atmospheric pressure at elevation. And I that seems to be how I function. I don't do well at sea level. I turn into a blobfish, like a blobfish out of water. This is one of the reasons I live in Colorado. But take me here, and I feel like my liquids, my water, my blood is flowing more efficiently through the tubes. I don't know if you have any on the spot theorizing about that.
Theorizing on what? On why your blood flows?
Yeah, why some people may benefit from living at elevation if our fluids are flowing faster through the tubes, right? Because a tube is similar to a tennis ball. It's not the same, obviously. One is air filled and one is liquid filled, but that's my theory, is that our fluids travel faster, and that's good for some people if normally they're sluggish, and it's probably not good for other people who maybe already their liquids are flowing faster, and then they come to elevation and it speeds it up even more.
Well, I'm struggling with that one. Yeah. I obviously haven't thought about it. Maybe I need to get back to you on that one after I've thought about it.
Yeah, I wondered if it had any bearing on. Maybe you could let us know about what you published in this paper about, fluids flowing through the.
Well, yeah, I think many people claim that they will perform better at sea level rather than an elevated level, because the PO2 is lower up there, and you breathe less oxygen, and you perform more poorly. And you're reporting the opposite, if I understood. You're at elevation. It seems that you feel better and you perform better. So it seems opposite what's reported by most people. And I'm not sure how to explain this, what seems like an anomaly to me, but it's not to you because it's what you feel. So it needs explanation. Are there other people who feel the same way, or are you unique that way?
My guess would be yes. And I started writing about this on Substack just to see if other people report similar things, and some people have. And I think it's just something we haven't talked about, really. But well, let's come back to. I don't want to derail you too much, and so maybe for people listening, if some of my audience will definitely be familiar with you, but some may not. So this idea of fourth phase water, easy water that we've been talking about, is, I guess, still controversial, although it doesn't seem like it to me in the circles that I run in, but it's certainly not been adopted worldwide. Maybe you could explain what fourth phase water is and why it's so important that we know about it.
What fourth phase water is? It's a phase of water in which the molecules are organized, as Gilbert Ling has suggested, but organized in a different way. So maybe it's best if I answer your question in the context of how we went about looking for it and what we found. That's probably the best way. Yeah. So we started with Gilbert Ling's idea. Gilbert Ling said the water molecules are organized in some way, And if they're organized, it's kind of like a crystal because one molecule builds on another. You can imagine water molecules are often treated as dipoles. That's like little beans with a plus in one end and minus at the other end. And you could imagine how they would stack, plus to minus. He said that's the way it is. And so we started with that premise. It's like a crystal. Now, crystals tend to be pure, like ice, for example. If you start with water that's pure, it turns into ice. If you start with water that's impure, first thing that happens is the impurities are excluded. Otherwise, you wouldn't get purity. So we were thinking if the water is like Gilbert Ling was suggesting, the solutes or particles or whatever ought to be excluded. So we're looking for this kind of exclusion, and we found it quickly. What we did is we took a bath full of water and we immersed microspheres, little tiny particles, spherical, about 1 micrometer in diameter, is widely used in science. We suspended these microspheres in the water. So we have a suspension, an aqueous suspension of microspheres. And then we immersed in that chamber full of water and microspheres a gel. And immediately, first time we did it, we saw a result which was really interesting, that next to every face of the gel, the microspheres tended to move out of the zone, and beyond. They were kind of pushed out next to every surface of the gel. And we tried many different gels. We tried other polymers, for example, biological surfaces. And as long as it was hydrophilic, in most, not all cases, most cases, the same phenomenon happened. So we began to call it exclusion zone because it excluded. Later, when we found that the water inside this zone is completely different from ordinary water, it had properties. Every property we looked at differed, and there were many, and other labs too. And we began to call it fourth phase water because it wasn't behaving like ordinary liquid water. It was, first of all, viscous, gel-like, and had many, many interesting properties. So that's where we started. We took off. Now, one question that arose, which turned out to be an important question, is are these exclusion zones neutral or are they charged? Now, we started with water. Water is neutral, and so we were fully expecting that this zone would be neutral because it grew somehow out of water. Well, it wasn't. It turned out, in most cases, not all, most cases, negatively charged. Now, how is it possible that this could be negatively charged? Well, we started with neutral water, and therefore, if you have a region that's negatively charged, you must have another region that's positively charged. So we looked for that, and we found that just beyond the exclusion zone, the negatively charged exclusion zone, just beyond it was a zone of positivity. So we have negative and positive. What that means is you got a battery. Now, and we demonstrated, showed proof of principle that this battery could actually deliver current. We don't know how much current, but we know that, we know how much current in a simple laboratory setting, and we don't know whether the amount of current is sufficient, for example, to power a city or something like this. That's yet to be tested, but, the proof of principle is there, and it remains to be studied and perhaps even exploited. So we have a battery, and if the battery exists in the body, then you can imagine that this battery may be supplying energy to the body. And that, of course, that intrigued us, but then a question arose. You can't get something for nothing, or some of us think we might, but most people think not. And in physics, people know that you can't create energy out of nothing. The only way you can gain energy is by converting another kind of energy to this. You have a electric range, and and the electricity is turned basically into heat. So electrical energy into thermal energy. And so we're trying to figure out what's building the energy, what's powering this battery. We couldn't figure it out. And one day I was in my office and an undergraduate comes knocking on my door. Yeah, I got to show you something. So I went in, and what he showed me is that he didn't admit that he was bored or something, but he was dealing with a chamber similar to what I described earlier. And he noticed next to him was a gooseneck lamp, and he wanted to try something. So he shined the gooseneck lamp, shined it on the chamber, and the region that was illuminated, the exclusion zone grew, and it grew by leaps and bounds. It was really, really, really quite a lot. And I said to him immediately, first of all, I'm thinking, my goodness, this guy's got the answer. Light is what's doing it. And it wouldn't be surprising because, in plants, first step of photosynthesis is light. Light comes in. It splits water into negative and positive, just pretty much as we found, which, may have important implications for what's going on during photosynthesis, the first step. And so, it didn't sound unreasonable. I said to him, well, why don't you turn off the lamp? He turned off the lamp, and the expanded exclusion zone went back to its initial position. So it became pretty clear that somehow light was responsible. We didn't know what wavelength of light, and the light bulb has a series of wavelengths ranging at the short end to ultraviolet, then intermediate to the visible spectrum, and then at the long wavelength and to infrared. UV.
No, I'm just curious. What was this at a time when we were mostly using incandescents, and does that matter?
It wasn't so many years ago because all of our experiments were done. I used to study muscle attraction, and I switched about a little more than 20 years ago. So, yeah, maybe I think it was an incandescent bulb. Well, anyway, whatever it was, we did experiments to figure out. We looked at all of those various wavelengths. So, for example, we started at ultraviolet light, short wavelength. Nothing, no expansion of the EZ. We looked at the visible spectrum, starting at violet and working our way toward the red, and very little effect, except when we got to the red, there was some effect. It was not dramatic. And when we moved to the infrared wavelengths, especially around 3,000 nanometers or so, we found a spectacular effect. A very weak LED lamp producing very little infrared, minuscule amounts, was able to expand the exclusion zone enormously. We could obtain up to 10 times expansion of the exclusion zone. So it's infrared. Infrared is all around us. Most people don't understand or don't know. We think infrared is somehow associated with heat. We think of the toaster. We push down the toaster. We see the coils glowing bright orange, and we say, oh yeah, well, it's producing infrared energy. But it's all around us. And if in your lovely room, you turn off all the lights, can't see anything, your cell phone camera records nothing. If you whip out an infrared camera, which is the same as an ordinary camera, except the sensor is sensitive not to visible wavelengths, but to infrared wavelengths, you get a beautiful image. I'd be able to see your earrings, the doorknob, the plant, whatever, everything, the microphone. And that's why the military uses it at night to look at the enemy, check out the tanks and whatever, because everything is generating infrared energy. It's all around us. And so it means It means that if you've got infrared energy, and you always have it, you could obtain more with certain sources, but you always have it, which means you always have easy water, not only in the cell, but everywhere. Anywhere you have a suitable hydrophilic surface and water sitting next to it, that water, if you've got infrared energy, which you always do, that water will turn into easy water. And if you add more infrared energy, you get a bigger easy. So that, that sort of summarizes some of the main features. And what I would like to emphasize is the energy, because this water contains energy. When you think of water containing energy, you say, oh, impossible. How could water contain energy? It's nothing more than, this substance that you drink, and I should drink more of, and can contain energy. Our body and the body of the jellyfish, full of water, and therefore full of energy. And I might, I complete this phase of our discussion by mentioning something that a lot of people don't know, which is highly relevant to what I'm talking about. And what they don't realize is that it was, I think, 1940 or 41 or so, that the idea of chemical energy comes from ATP, comes from a high-energy phosphate bond contained in ATP. And that was exciting news, and it crossed the oceans and the rest of the world very quickly, and pretty soon everybody's really excited that finally the source of your energy and my energy is known. What people don't realize is that view is challenged. And I actually know the challengers. They happen to be in the muscle field. And these are astute scientists. And they found it was, I think in the 1950s, they studied very carefully about ATP, high energy. They found there's no high energy phosphate bond, that all the bonds are just like other organophosphate bonds, nothing special. And they were a little bit diffident about suggesting the implications of their finding. But here we sit with one paper from 1940 establishing or suggesting that we know the source of energy, and another one saying, no. It didn't say it exactly in those words, but they found it's not true. So we don't know where truth lies. Is it the challengers who are right, or is the original finding that's right? It's desperate that these experiments be repeated, because there's a possibility that ATP, high energy phosphate bond, is a red herring. It could be completely wrong. I'm not saying that it's wrong. I'm saying that it needs to be investigated. If it's wrong, then you need another source of energy. Well, a possible source of energy is what I've been talking about, water. Water is in every living creature, and we demonstrated that water contains energy. And in every cell of the body, each cell is negatively charged. And those negative charges, all they want to do is get away from each other. They're repelled. And so if you start with a high concentration of negative charge inside every cell, that's potential energy. And that energy can get released in terms of facilitating work inside the cell. So I'm not opining that this is the answer. I'm suggesting that it's really important to look in to see whether it's really chemical energy from ATP that runs our bodies, or whether it's electrical energy, or some combination of the two. Right now, unknown, needs to be known. But the important point is that, water is an energy source. It's not just bland liquid. And if it's an energy source, then, usually Mother Nature doesn't throw away energy. If it's there, it uses it. So I guess I should stop in my long diatribe, but you asked me, what is easy water and why is it important? I tried to answer that.
No, that's wonderful. It's a perfect segue, actually, to what I had mentioned in my email to you that I'd love to talk about, which are the 5 kinetic energies, because that does seem very important to me, and it's something I love looking into and talking about, working with the people that I work with, or just to understand our body. Because the way that I interpret what you're saying in total lay language, not non-scientific, is that water maybe is an element that can harness energy, that can store, as you just said, potential energy, that also can, depending on what it's exposed to, right? Infrared light, for example, perhaps create energy. So it's an absorb. So if we're talking about the human being, then we can absorb energy, so we can harness energy, or our body can. And then we can transform it. And when I look at all these energies, they seem to be interconnected and kind of always in phases. And you talk about 4th phase of water. They're always in processes. If we're stagnant, then we're probably unhealthy. So we've got thermal energy, or radiant energy, light energy, coming into the body or water, and creating then electrical energy potential. And then that maybe is harnessed through mechanical energy potential, which produces thermal energy. And then thermal, of course, emits some radiant energy, and then we have light again. And so it's this cyclical. How would you describe that in terms of, what's going on with us in terms of water being that it seems to facilitate? Is that the right?
I'm not sure. Yeah, maybe facilitate, or it's step one. You got energy, and depending on the particular need of the body, that energy is then transformed into mechanical energy is the one primary feature. Maybe it's because I started my career in muscle contraction, where the muscle is actually delivering mechanical energy. And so if you trace the energetic pathway, you start with radiant energy that creates electrical energy that transitions into mechanical energy. So the body is full of these kinds of transitions. And another one is flow. Flow is extremely important, not only in the cardiovascular system, but in fascia and in lymphatic. There's no real understanding of how flow occurs as lymph. What's driving it, and what we found as a driver of blood, probably also as a driver of lymph, and all kinds of flows. There are all kinds of flows in animals and plants that are occurring, and nobody really understands how they occur. One theory is that they occur the same way as muscles contract, but the evidence for that is not so clear. And I think water could be an important mediator, or maybe better verbalized as a source of energy, which then gets transformed into any and all kinds of energies that the body uses for whatever it is.
Yeah, and I've heard you. Would you speak a little bit about the exclusion aspect of this easy water? Like it excludes, I guess, chemicals, and then of course we could label it a toxin, but it sort of acts as a filtration system as well.
Absolutely. So this is in the practical vein. We don't tend to focus so much on practical stuff. We focus on fundamentals. I have a hunger and desire to find truth in nature, wherever it may lie. You opened the door. This book is coming next, and this is a pre-publication version with a black and white cover. That just the book will be published in a few months, and it's again heading toward finding truth in nature, and and there are a lot of things that occur in nature that we think we understand, but when we dig down beneath the most superficial level, we find out we really don't understand it. It deals with many topics, and the topics range from, for example, gravitation. So we all know that masses attract one another, but then you ask the next question: why do they attract? No idea. And so the question is that the real mechanism? And all the way to questions like, how do birds fly? And if your kid asks you, or grandchild, depending on your age, how do birds fly? And the usual response is, well, they flap their wings. But every day, I'm sitting in my house right now, and every day I look at the eagles that are flying, and they may flap their wings on occasion, but mostly they don't. And they can fly for long distances, either going level or going up or going down, with the wind, against the wind, doesn't matter. So that explanation doesn't suffice. And I go into some explanations of, I think, of how they really fly, and it does have something to do with electrical charge. So the electrical charge issue has brought me from cell biology to trying to figure out so many things in nature that we see every day, but we really don't understand. So I'm having fun with that. Now, I've deviated from your question. Would you please repeat your question?
I don't know. It doesn't matter. I'm very excited to read your new book. Yeah, so I'll have to.
It will be published in a few months.
Wonderful.
And I'm really excited about it.
Well, so what are some implications of our misunderstanding of energy currently? I've heard you mention cancer, for example, having not having that negative energy potential charge to it, and other. I'm sure there are, as you said, in nature, many things we don't understand.
Well, the implications for cancer, cancer has been studied now for obviously such a long time, and our President Nixon, if you pardon the expression, declared war on cancer, and that was more than 50 years ago. And I think many would agree that the war has not been won. We got to figure out. And if you think about the studies of cancer, mostly they've been oriented toward genetics, oncogenes and such, and maybe that's the wrong direction, because that direction has been in place now for half a century, and we haven't solved the problem. So, who is it who said the essence of mental illness is to beat your head against the wall continuously and expect to have a different outcome. Keep doing it, and so the new revelations about water bring to mind a different possibility that somehow water could be related to cancer, and you wouldn't think so. However, I think there is a link, and I've been discussing the link, and my manuscript has been getting a lot of attention, even though the manuscript has not yet been published. It's really hard to publish a manuscript when you're suggesting something that runs so obviously against the mainstream thinking. But anyway, if you like, I summarize in a few minutes what the idea is. Yeah, okay.
Please.
So if you think about the electrical potential of the cell, that's the critical feature. The electrical potential of the cell. Every physicist, biophysicist, biochemist will tell you it has to do with membrane pumps and channels. And I've argued that the electrical potential doesn't come from that. I've argued in various places for a half dozen different reasons. I'll just mention one reason. If you take a cell, and the argument is that the negativity inside the cell is due to the membrane, which has pumps and channels, and pumps negatively charged ions into the cell. And the mechanism actually is very complicated, but that's what the world thinks. Well, it's interesting in that vein, if that's true. If you strip off the membrane, you expect no electrical potential. Well, that has been done in some ways, and it has, in fact, no immediate effect on the electrical potential. But even more than that, if you just take something that resembles the cytoplasm of the cell, but without a membrane, for example, like raw egg white, it's a gel, but it's the cytoplasm of the cell. If you take gels, and various groups have done that, including our group, you stick an electrode in the cell, you measure pretty much the same electrical potential as you'd measure in a cell with a membrane. But here, you've got no membrane, no channels, no pumps, but the same electrical potential. So it's kind of hard to say that in the cell, the electrical potential comes from some membrane stuff. So I've argued that the cell is full of easy water. It needs that easy water to function. And easy water is negatively charged. So, it's very simple. You have a bag full of something that's negatively charged, and you stick an electrode in and you measure negative electrical potential. That's okay. So now it turns out that studies by a guy named Clarence Cohn and duplicated many times. This is 50 years ago. He showed that if a cell is to divide, cancer cells to divide all the time. And if a cell is to divide, what it needs is a small electrical potential, low electrical potential. And it's a bit confusing in terminology because we're talking about negative potential. I'm talking about the magnitude only. So if you have a low magnitude electrical potential in a cell, like minus 10 or 15 millivolts instead of minus 60 or 70 or 80 millivolts, then the cell divides. It doesn't matter if it's a cancer cell or embryonic cell, which divides naturally. They all have small electrical potential. And cells that don't divide have large electrical potential. And this guy, Clarence Cohn, demonstrated that if you undertake maneuvers that polarize the cell even more, give it a bigger electrical potential, it'll never divide. So that's really important. And a review article shows that it's true in many, many cells, whether they're cancer cells or non-cancer cells, embryonic cells. In order to divide, they need to have a small electrical potential. Now, what does that mean? Well, if the electrical potential is due to easy water, and you have a small electrical potential, it must mean you're missing a lot of easy water. And the cell can't function that way, and many pathologies arise, including cancer. And so the implication is that this needs testing, obviously, but the implication is if we're on the right track, then it's not complicated to reverse cancer. All you need to do is build easy water. And I've talked about, a half dozen simple expedients that help build easy water. One is to drink water, drink a lot of water, keep yourself hydrated. But there are other simple expedients. Expose yourself to infrared energy, builds easy water. And some of these methodologies have actually been used successfully. So I think we might be onto something. It would be great to be able to study this in the lab, but studies of this nature require money because you need to hire the people to work in the lab, and they need to put bread on their tables. They need salaries, and when you're espousing something that challenges mainstream views, getting funding is really hard. I spend a good deal of my time trying. We have some funding, but it's modest funding. And so this is the limiting factor. I think we have something really promising, but in order to study it, we have to figure out how we can keep the lab funding and going.
Yeah, this is one of my I feel like an evangelical, this is one of my missions is to figure out a way to get everyday people to want to fund science like this, whether it's and I'll just be honest about my opinion. To me, science is science. It doesn't matter who's doing it. You don't have to be, have someone tell you can be a scientist because you have a certain degree. We can all participate in science, I think.
Well, the evidence that you're right, I presented in our discussion because I talked about 3 young undergraduate students who are obviously not scientists, and some of the most important findings came from those students. So absolutely, I'm right with you on that.
Yeah. So, it's a shame that all the money is going, of course, to all the corporations that want to make even more money on the things that don't really work, even. But they tend to make a lot of money.
Well, we're operating on the same wavelength.
Yeah. Well, I know you have to run soon. I'm wondering, in closing, if there's anything that you've wished that people have asked you that no one has asked you yet.
Boy. That's a question that I've never received before. I've done a fair number of podcasts, and nobody has asked me before. Answering that, I think, requires a bit of
more time,
a bit of thinking about it. I guess I would like to say a few words, philosophical words, that we're not. The world is not doing much in the way of fundamental science anymore. Fundamental science is in decline, and I think maybe I don't really. It's not my intention to pat myself on the back. I'm eternally curious. I want to find out, how nature works, all the way, from the organism level all the way down to the atomic level. And I have a book that's almost ready about the structure of the atom, which I think is actually wrong. It's different from what we think, and I guess it's taking a risk to do that. I don't know. Maybe I was just born as a risk taker, but I think there are a lot of people who have a hunger, desire to figure out what's going on. It's natural that we want to figure out what it is around us that it bears responsibility to the things we see every day. But the system that exists today doesn't really encourage us to do that. And you know better than I do about all the restrictions that exist. I guess I would close by saying that I would encourage people to do that, to take the risk. You may have something to lose, but what you have to gain is enormous, because the pleasure of discovering something is absolutely immense. Such enormous gratification from chasing the absolute fundamentals in nature, accept nothing that doesn't seem reasonable, and dig beneath the surface to find out the real fundamentals of nature. It's completely gratifying. And I should add an addendum to that. There really is one organization that we devised to respond to the restrictions on exploring fundamental science. It's called the Institute for Venture Science, ivscience.org. IV like intravenous, but Institute for Venture Science, ivscience.org, not .com. And take a look at it. And we're, of course, trying to raise money. And the idea is to fund the most promising ideas that challenge conventional wisdom. We think we have an idea of how to do this, how to restore science to the way it once was. 100 years ago, there was, one Nobel Prize after another in fundamental physics and such, and we're not doing that right now. Almost no revolutions. We need revolutions badly, and it's the system of getting grants, and the grant application is reviewed by the person you're challenging. They get the experts to make judgment, and that doesn't work so well. So
wouldn't it be wonderful if we could inspire a whole generation of young people to want to actually do that science? I think that would be fabulous.
I agree with you fully. Yeah, if we can do that, I hope we can do that. It's a real task. I think we need an ambassador, someone who really speaks well for science, and mostly we need money to support it, because you can't do anything without money, unfortunately. So that's, I guess, you might say, a closing message. Yeah, I'm sorry. This discussion could go on for a long time, but I've got some commitments, and so I apologize for that. But it's been really intriguing discussing with you, and I really appreciate the opportunity.
Well, maybe we can do it again.
Absolutely, happy to do that. Or next time I pass through Denver Airport, where there are often delays, maybe we can connect.
Oh, that would be wonderful. Please reach out. And I will reach out to you again if you're open to that, because I would have you back on anytime. This is a passion of mine, to get real living science out there. I call it living. I actually just started something called the School for Living Science. I want to inspire everyday people to think scientifically about their own health and how they function, and observe, the natural phenomenon, and think it through and form theories. And so I love what you're doing, and I think we need as much of this as we can get in the world. And so I'll maybe end the same way I started, and just thank you again. Thank you.
Well, and thank you so much for the opportunity. I really appreciate it.
Yeah, just real quick, if people you mentioned this one website, and if people want to learn more about you, they can go to that website to help fund it. And is there anywhere else you would send them?
Well, yeah, I was in two places. First of all, our lab website, pollacklab.org.
Simple. We'll put that,
one word, .org.
Okay.
And the essence of many of the things I've been talking about is in the book called The Fourth Phase of Water. And you just check on Amazon, and the reviews are well, how should I say, comforting. Anytime I'm feeling kind of down, I look at the reviews, and there are some people who appreciate what's going on. The reviews are very nice.
Well, I'm one of them. I highly recommend the book to everybody. Thank you so much, Jerry, and I hope we can do it again.
It's my pleasure. Okay, take care.